Alrighty, let's get started with chapter 2. So as you can see, we're talking about atoms, molecules, and ions. So the first thing we want to start with is some fundamental chemical laws, such as the law of conservation of mass. So the law of conservation of mass is it's roughly however many atoms, however much mass you start with is what you have to end with. So mass is not created or destroyed. I've given you a couple of reactions. Uh, Continuing on with common reactions that you'll want to be picking up as we go through this class uh, and then also second semester. Here's one of the gas forming reactions. And you see here, I've given you the reaction, the chemical reaction equation. So there's your chemical reaction equation. But I've also given you a schematic to show you what this reaction is. This version of a gas forming reaction is going to be an acid or a carbonate. You can also have an acid or a carbonate or a bicarbonate. Those will combine to form salt, water, and carbon dioxide. And now remember, salt is an ionic compound in chemistry. It's uh, it's ions of different charges coming together to form a neutral species. So let's look at this. In this case, you notice that our acid is HCl, and so that's hydrochloric acid. These names you'll pick up as we go along. Now, you see a new phase here we'll talk about more as we go along as well. So you see the aqueous phase, we've been dealing with solid, liquid, gas. Aqueous is going to mean dissolved in solution or dissolved in water. So next you have your carbonate. So here, and we'll get to naming by the end of this chapter. So that is calcium carbonate. And in particular, you notice the carbonate polyatomic ion. I want to give you a list of polyatomic ions. Really, the best way to go about them is just to start memorizing them. So you have your acid, hydrochloric acid, plus calcium carbonate is going to yield your salt, which is calcium chloride, and that's so you have your +2 calcium, your -1 chlorides. They come together to neutralize to form calcium chloride. Then you have your water, your H2O, and your carbon dioxide gas, which is CO2. So a gas forming reaction. And you have both the structure of it and then an actual reaction equation. So let's take a look. So how does this match up with conservation of mass? Well, let's see. I have two hydrogens, uh, two chlorines, calcium, calcium, a carbon. I have a carbon, and then three oxygens, two, three. So you see all of the mass is preserved. We had a chemical reaction to form new compounds, but the mass is conserved. Here's another example. This is another form of a gas forming reaction. So again, you have the schematic, which is ammonium salt. Ammonium, again, is one of your polyatomic ions. Ammonium salt plus a strong base is going to yield salt, water, and ammonium gas. So this is another schematic for a gas forming reaction. So here, your ammonium salt is ammonium chloride. And again, so ammonium is a +1, chloride is a -1. You see that those equal each other out, so you have a salt compound. Your strong base is sodium hydroxide, and those come together to form your new salt, which is sodium chloride or common table salt, water, and ammonia gas. And again, you can see what we have a nitrogen, sodium, chloride, a chloride. One, two, three, four, 5 hydrogens, 1, 2, 3, 4, 5, and an oxygen and an oxygen. So once again, mass is conserved. Down here at the bottom of this slide, you see the methane combustion reaction. Again, a very common format. Combustion always has to have oxygen. So methane plus your oxygen, add heat. And you're going to get carbon dioxide and water because, of course, your methane is a hydrocarbon. So again, if you see a compound that is dominated by uh, carbon and hydrogen, and that's going to be a hydrocarbon. Compounds that also have oxygen in them will yield the same results over here, but your hydrogen carbon mixture is your hydrocarbon. And this one you can see pictorially, and you can count up all the atoms. You can see how they're preserved. The total mass is preserved on both sides of the reaction equation. So law of definite proportions. So for a molecule to be what it is, it has to come in certain proportions. So here you see the C2H6, that's ethane. So ethane, so eth is a prefix meaning two carbons, whereas meth is a prefix meaning one carbon. So you notice here that ethane is C2H6. You always have to have that two carbon, six hydrogen ratio. Now, and you don't think of it with this law, you don't think of it in terms of atoms. You think of it in terms of mass. You have to have a 6-to-2 ratio of the mass of hydrogen to the mass of carbon uh, in your compound for it to be ethane. You know, it's actually not 6-to-2 that way. The law of definite proportions has to do with you have a specific proportion of elements by mass for it to be a certain compound. Again, with the methanol, you have to have a specific proportion by mass for this to be for this to be CH3OH. The reason I'm backing up on the ethane is because hydrogen is 1.01 grams per mole, carbon 12.01 grams per mole. So six of these would be 6.06, and then two carbons would be about 24.02. So actually, in this case, the carbon has about 4 times the mass as the hydrogen, but it has to you're going to have to end up in that ratio. And then once you know what the masses of each atom is, you can end up with the molecular formula or the chemical formula for ethane. But you're going to have this ratio of masses for it to be ethane. Now, law of multiple proportions. This is where we'll do a little math. So anytime you have elements that come together to form different compounds, here you see different combinations of nitrogen and oxygen. When you compare the uh, the second element to the first element, you hold the first element in the compound at 1 gram. So in this one, you see that nitrogen is going to be your element that's held at 1 gram. So in every single compound that combines nitrogen and oxygen, your ratios of your oxygens. So first, you're going to have a mass ratio between oxygen and nitrogen for each compound, but then what you're really looking at is the ratio of your oxygen to your oxygen between the two compounds. And what you'll notice is when nitrogen and oxygen come together to form multiple compounds, and you start taking the ratios of your oxygens here, which is your second element, held in comparison to a constant 1 gram of nitrogen, you're going to start to notice, like, for example, these two compounds have a 1-to-2 ratio for the oxygen. So you're going to get these whole number multiples when you go from compound to compound. Keep in mind, ratios can also work like fractions. So a lot of times you see the colon used, but uh, in this case, it can also be viewed as a fraction. But like what I was talking about, if you look at the two different compounds that are represented here, 1 and 2, and you take the ratios of the oxygens, because both of these are are compared to a common 1 gram of nitrogen, you see that we compare the 1.14 grams of oxygen in one compound to the 2.28 grams of oxygen in the other compound, and we get the 1 to 2 ratio. So let's kind of look at this. Here's several compounds containing sulfur and fluorine. 3 of them have the following compositions. So molecule 1 is 1.188 grams of fluorine for every 1 gram of sulfur. So first off, notice that your sulfur is your 1 gram comparison. Your second compound has 2.375 grams of fluorine. The third compound has 3.563 grams of fluorine. We want to show that these 3 different compounds, which are different combinations of sulfur and fluorine, uh, coincide with the law of multiple proportions. Okay, so what is this problem asking us for? Well, to know if this matches the law of multiple proportions, we are going to have our ratios. Now, things that I know, compound 1, 1.188 grams of fluorine. Compound 2, 2.375 grams of fluorine. Compound 3, 3.563 grams of fluorine. And then sulfur is our reference atom. Okay, so those are our known values. So let's do our first ratio. So we are going to do compound 1 ratio to compound 2. Okay. So what we're comparing, of course, is the fluorines, because sulfur is always held at 1 gram. So when I compare the fluorines of 1 to 2, that becomes a ratio 1.188 grams to 2.375 grams. Now I'm going to divide through, and you want to divide by your smallest number so that you're dealing with numbers that are greater than 1. Okay. And what I'm going to end up with is I'm going to end up with 1 to 1.999. Now, a lot of times when you're doing calculations like this, you're going to notice this same thing with, for example, empirical to molecular formulas or empirical formulas, so on and so forth. When you get a number like this, your 1.999, you're going to round to the nearest whole number. So what you're going to get is a 1 to 2 ratio. So you notice that, of course, your ratio between compound 1 and compound 2 is a whole number ratio for your fluorine. So that those two obey the law of multiple proportions. What about ratio? So we're going to do another ratio. So this is going to be compound 1, compound 3. Okay, so now we're going to use the ratio of 1.188 to 3.563. Going to divide through by the smaller number. And now, could you divide through by the bigger number? You could, but you're going to end up with, on the side where your 1.188 is, you're going to end up with a number less than 1, and then you're going to have to find a way to move both of those to a whole number. It's just easier to do it by dividing by the bigger number. So then what you're going to get is a 1 on the left side, and on the right side, you're going to get a 2.999. And when we round to the nearest whole number, we're going to get a 1 to 3 ratio. So those two obey the law of multiple proportions. We need to do a third ratio, though. You need to make sure you check every pairing. So for this one, we are going to do compound 2 to compound 3. And so that is going to be that number and that number. Okay, so this is going to give us 2.375 grams of fluorine to 3.563 grams of fluorine. I'm going to divide through by the smaller number. And what this is going to give me is now this is interesting. You get a 1.5 ratio. Okay. So this doesn't mean that this necessarily disobeys the law of multiple proportions. Well, we notice though that we can turn this into a ratio of two whole numbers if I then multiply by 2. So that if I multiply 3 by 2, it's going to give me a 2. Then 1.5 times 2 is 3. So I get a 2 to 3 ratio, which obeys the law of multiple proportions. And so again, what this is showing you is when I compare fluorine to sulfur in these various compounds, I'm showing that when I hold sulfur as a reference atom, the fluorines are going to combine with the sulfur in whole number ratios to each other, compound to compound. And so that's your law of multiple proportions. So your total ratio is going to be 1 to 2 to 3. So yes, these whole number ratios do show that these molecules follow the law of multiple proportions. So here's another one. You might want to shut off the recording and try to work through this one. Otherwise, we're going to go ahead. Okay. So both ammonia and hydrazine. Here you see we have molecules that are combinations of nitrogen and hydrogen. Are composed of, ammonia contains 0.2158 grams of hydrogen for every gram of nitrogen. Hydrazine contains 0.1439 grams of hydrogen for every gram of nitrogen. Show this is consistent with the law of multiple proportions. Okay, so again, trying to find our ratios. Let's see. Okay, so what are things we know? Nitrogen is our reference molecule held at 1 gram. For ammonia, we are going to get 0.2158 grams of hydrogen. And for hydrazine, we are going to get 0.1439 grams of hydrogen. There's the things we know. Okay, now, when we want the rate, so the ratio we're looking for here is NH3, so ammonia, the hydrazine, and we're working with the different hydrogen masses. So what this is going to give us is our 0.2158 to 0.1439. So I'm going to divide through by the smallest number. Okay, and this will give me 1.4997 to 1. And when I round to the nearest whole number, I'm going to get 1.5 to 1, which we know how to deal with now. So we're going to take this, multiply it by 2, and we're going to get a ratio of 3 to 1. Nope, hang on. I did that wrong. 3 to 2. There we go. So first off, we can see that this does match the law of multiple proportions. We end up with this nice whole number ratio. So let's look at another reason this makes sense. I'm going to do this in a different color because this is not part of your answer, but we can make sense of this law. So in ammonia, the ratio of nitrogen to hydrogen is 3 hydrogens to 1 nitrogen. In hydrazine, well, we have to think about this because that hydrazine, I can actually turn this into an empirical formula. So if I divide those subscripts by 2, I end up with NH2. So you could say this ratio starts out at 4 to 2 and then goes to 2 to 1, or you could just divide through, divide each one of these by 2, get the NH2, and then you still see the ratio is 2 to 1. In hydrogen to nitrogen. So you see both nitrogens are a 1, but what's the ratio for the hydrogens? Well, the ratio for the hydrogens is 3 to 2 between the two molecules. So we can make sense of this in another way. All right. Early experiments to characterize the atom. This first one here was done by J.J. Thomson. It was discovery of the electron. Uh, he worked with devices called cathode ray tubes, where you'd have a cathode or the negative electrode, and you would heat it up, and it would fire off, well, what we know now to be electrons. And those would pass through an anode, and they were then pulled towards the cathode, which is the positive. Cathode's negative, anode. They're pulled towards the anode, which is the positive electrode. And the electrons were pulled towards the anode because the anode by an electric field. So the electrons they're negative in charge. They're going to be attracted to the positive plate. And and of course, this was how he realized that this was a beam of negatively charged particles because they were repelled by the cathode, attracted by the anode. And then, of course, he did some more experiments to figure out, for example, the charge to mass ratio of the electron. And so he did this so first off, he would have he would have plates where he would have an electrically charged plate putting out an electric field, and then he would have a magnetic field. And the magnetic field and the electric field would be set up in a way where they would completely cancel each other out, and the beam would fly straight. Then, of course, the magnetic field would be turned off, and the electric field would be allowed to displace the electron beam, and then he would measure that displacement. He first had to have them equal so that he could get the velocity of the electron. He couldn't just go straight to electron displacement. But through all that, he came up with this charge to mass ratio. So Q over M is going to be 2ye over b squared L squared. And of course, what we get here is y is your distance that's your electron beam is deflected. And that's just because it's on the y-axis. B is your magnetic field. L is going to be the length of your electric field plates. So keep in mind, like your electric field plate, your electron's only going to be deflected while it's subjected to the electric field from that plate. So it's only going to have an electric force put on it across the length of that plate. E is your electric field. Q is what you see used in physics commonly to represent charge, and M is mass. So let's kind of think about, let's do a little physics real quick. So when the beam is straight, what happens? So we have our electron. And then we have two force vectors applied to it. So of course, that's our electron. And here we have a magnetic force vector. Down here we have an electric force vector, and they're equal. So the beam flies straight. It's not going to be deflected one way or the other. So in physics, what we do is we say, well, let's try and get an idea. And this is how he figured out the velocity of the electron. So we're going to say, let's work with the sum of these forces. So remember your sigma, your capital sigma is a sum. The sum of your forces, and you have however many forces. In this case, it's only two forces. That's going to be your magnetic force plus your electric force, and that's going to equal 0 because, of course, you see those two vectors pointing in the opposite direction, and they cancel each other out. So what does this mean? This means that your electric force is going to end up equaling the negative of your magnetic force. And something you'll learn later when you take physics is what this notation, the arrow over the top of the F, is it represents a vector. But you don't have to. I'm just showing you where this comes from, working through some more mathematical logic that I encourage you to work through on your own and look up some of the terminology that I'm giving you, like sum of forces, magnetic force, electric force. And when you're in physics, second semester, you end up learning that each one of these has an equation represented that represents it. So on the left side of the equation, you end up working through Coulomb's law, and your electric force ends up equaling Q times E, which is your charge, times the strength of your electric field. On the right, you end up working through the Lorentz force, and you end up with Q VB. So charge times velocity of your particle times the magnitude of the strength of your magnetic field. And so the first thing we can do, we can divide through by Q. That's going to eliminate Q on both sides. It's going to be E equals V times B. And so the velocity of your electrons ends up being your electric field divided by your magnetic field. And so now that you have that, now the magnetic field can be shut off and the electron can be allowed to deflect. So bear with me, my three-dimensional drawings are never great, but let's see here. Going to have a positively charged plate. Of length L. Then we're going to have our electron. The first thing I want to do is the electron's moving in that direction, and we're going to say we always want to set coordinates, so the x direction and the y direction. And what you're going to get is your electron's going to start there, and then it's going to move, it's going to start to deflect like that. Not the greatest drawing, but you get the point, because what we want is that distance there, your delta y. And so at this line, y, at the line there, y equals 0. So now we have these things called the kinematic equations. Okay, and so in the y direction, and these are something, again, you don't have to know now. You'll learn this when you get into physics. Kinematic number 1, change in y, v0y, or 0, so your v, anything with a sub-zero is initial. So that's your initial velocity in the y direction, times time plus 1/2 acceleration in the y direction, t squared. Okay, and the first thing we can say is v0y times t becomes 0, because initially the electron's moving in just like horizontal in the x direction. So there is no velocity in the y direction. So our delta y, of course, is going to be our y minus y0. So our initial point for y, or final minus initial, then we're going to have 1/2 ay times time squared. And of course, that line is y equals 0, so that becomes 0. And so we're going to end up with our position y, whichever side you put the positive plate on to deflect the electron, you're going to have 1/2 ay t squared. Then we need to think about, because we don't have a time, so we need to replace that with something. So let's do the same kinematic in the x direction. Well, this time, this term becomes 0 because there is no acceleration in the x direction. The electron's just moving in the x direction, but nothing is making it slow down or speed up. So there's no acceleration. And so then your delta x becomes L. So your change in x is going to be the length of that plate. That's how long the electron was deflected, was across the length of that plate. And that's going to become the initial x times time. And so we get an expression for t. We're going to cut off the subscripts for velocity because we're not so much worried about it split into x and y. That's going to be the main velocity of the electron. So we have L over V. Keep in mind, I'm doing a short derivation here, things you can look up and follow along with. When you go into physics class later, we will do this more in depth. And so it'll make more sense then, but I'm giving you just enough to follow to work on your mathematical logic, which is something you're supposed to be building. Now, we also need an expression for our acceleration. And for that, we're going to be using Newton's second law. That's going to be your electric force is going to equal the mass of your electron, mass times acceleration. So mass of your electron times the acceleration in the y direction. And we know that that equals q times e. So our acceleration now is going to be q times e divided by the mass of the electron. Now we have everything we need. And we're going to take this expression here and plug everything into it. Our expression for T, our expression for A. So Y is going to equal 1/2 QE over the mass of the electron times length of the plate over velocity squared. So of course, this is going to equal, let's see here. I'm going to multiply the 1/2 into here, and then I'm going to square this. So that's going to be QE over 2 ME times, and the way squaring both of those works is you just square both of them. L squared over velocity squared. However, since our velocity, you remember, go back up, is E over B. Velocity squared will be E squared over B squared. And now I'm going to have to substitute that in. I'm going to take this, substitute it into there. So now my Y is going to be 1/2. No. QE over 2 ME times L squared over E squared over B squared. Now, you see we have a fraction in the denominator, so we're going to flip and multiply, which is going to equal Q times E over 2 ME times L squared B squared over E squared. Okay, now I notice that I can do some canceling. That E there is going to cancel out the squared. And what I'm going to end up with is Y. I'm going to cancel that out and then multiply. So I end up with Q L squared B squared over 2 times the mass of the electron times E. Now what I do is I end up solving for Q over M. All righty. So let's just go ahead and I'm gonna flip these around. Everything's gonna retain its sign. So when I flip these, let's go ahead and write it out so we see what we're working with. What I'm going to do now is I'm going to multiply through by 2e. Because we're trying to ask, we're trying to, oh, I lost the word. Well, we're trying to get Q over M by itself. I had a bigger word in my head and it went out. So, because we're looking for the charge to mass ratio. Okay, so that means now we're going to have 2ye. Now what I want to do is divide through by L squared B squared. So we're going to end up with Q over the mass of the electron is 2YE L squared B squared, which of course, when we go back up, this is uh, exactly what Thomson found when he was working with these cathode rays. So again, what I've done here is it's a very simplified version of a physics derivation using some laws. I told you what those laws are. You can look those up. I want you kind of working through this and starting to understand where this stuff comes from. This is called modeling. You're trying to model things mathematically. Now, of course, there were things I didn't take you through, like the Lorentz force, uh, like Coulomb's law. Those are things you'll do later. But also, start thinking about things in terms of diagrams too. So these are your this here is a free body diagram, and then down on the bottom you have a diagram to explain the displacement of the electron under electric force. And so you're also going to want to try and understand things through diagrams. It's a new way of thinking that you may have done before, you may have not, but it's time to start doing it now. Okay, and so that charge to mass ratio ended up being a negative 1.76 times 10 to the eighth coulombs per gram. So that C there, that's a unit called coulombs. It's the SI unit for charge. Its best units to think of is going to be joules per volt, and we could break apart joules, but so on and so forth. So the J is joules. But yeah, your coulomb is your SI unit for charge. And then further on, through the experiments of Robert Millikan, through his famous oil drop experiment, he figured out the charge and mass of the electron. So the charge of the electron, now pay attention to some how we're labeling these. Your electron is a negative E. Actually, that's not quite right. We should call it, well, we'll do that in a minute. I called it negative E because E is your fundamental charge. And so both your proton and electron have a fundamental charge of E. It's just one's positive, one's negative. The symbol for the electron we'll be using later is E negative, whereas protons will be P positive and neutrons will be N zero. So this is a negative of that fundamental charge, and that's your electron. The mass of your electron is 9.11 times 10 to the negative 31st kilograms. So now through all these experiments, we have an understanding of the electron. But then there was another phenomenon that they noticed called radioactivity. So this was discovered by scientists like Henry Becquerel and Marie Curie in the 19th century. And they noticed that elements gave off high energy radiation, and they referred to this phenomenon as radioactivity. Now, three types of radiation were noticed. And so these are your Greek letters. Gamma rays, alpha particles, and beta particles. Now, gamma rays are they're high energy packets of electromagnetic radiation. They're photons. They're not solid particles like protons or neutrons. So, like, there are materials that will stop alpha particles and beta particles, but gamma rays go through everything, including a wall of lead. So you notice gamma rays way down here at the end with an extremely tiny wavelength. So that very, very tiny wavelength makes these rays very, very energetic. And plus that tiny wavelength allows them to pass through most materials. Alpha particles come from what's known as alpha decay. And so alpha decay is where an unstable nucleus will eject an alpha particle and transform into a new element in the process. So alpha particles are the nucleus of the helium-4 atom. Now, pay attention to what I wrote there, helium-4. So that is what's called an isotope name. So when you're naming isotopes, you want to have the element name and then the dash, and then you want to have the mass number. Because here you see the mass number, the 4, that's why we call it helium-4. We're going to go through that in a minute, how isotopes work, but just pay attention to the naming scheme. So for example, let's take a look at the alpha decay of polonium. And we want to go through the basic equations. And so what we have is, let's just start with polonium 210. So that's PO. And so now I'm using isotope notation. So the mass number's up top. Now I need to find the atomic number, 84, which is right there. Now what's going to happen is this is going to alpha decay. And the first thing we are going to get, this helium-4 isotope, this helium-4 nucleus is your alpha particle. And it really is just a nucleus. There's no electrons on it. It's just 2 protons, 2 neutrons. So yeah, 2 protons, 2 neutrons. And then what's going to happen is this is going to decay. So you have a 4 taken out of the top, a 2 taken out of the bottom. This is going to decay into 82, 206, because 210 minus 4 is 206. 84 minus 2 is 82. And then I say, well, what did it decay into? What element is element number 82? Well, it's lead. So I know some of this is new stuff, but that lower number in your that lower number in your isotope notation is your atomic number. Your atomic number is what tells you which element it is. That top number is your mass number, and we're going to define it here in just a little bit. But this is an alpha decay. So you can see the polonium decays into the alpha particle and lead 206. So here you see your mass number. That mass number is your isotope. And so this would be lead 206 if we wanted to name it. All right, so the next kind of decay, next kind of radiation is beta decay. Okay, beta decay is where you have an unstable atom, and it's either going to go through a beta negative, beta positive, or beta positive decay. The beta negative decay is the matter decay. The beta positive decay is the antimatter decay. Okay, so what you're going to get in your beta negative is you're going to get a new element. You're going to get an antineutrino and a very high energy, very fast electron. So this is called, that's your beta particle right there, that electron. And so the way this works, okay, and I'm going to be using some very generalized isotope notation. So once we cover isotopes, come back and look at this. It'll make more sense. So you have your element, Z and A. Z is your atomic number. A is your mass number. This is going to decay into, so your beta negative has the format of forming Y, which is a new element, Z plus 1, mass number stays the same, plus your beta particle, which in particle physics we denote as a -1, 0. It doesn't have an atomic number of -1. It's a high energy electron. We just use a -1 as a way to keep track of charges in the equation, and then plus your antineutrino. So That, so this shape, this symbol here, that is your Greek letter nu, and it is the symbol for neutrino. And with the bar over the top of it, you get an antimatter particle. It's a little hard to read. I should have given myself more room. Let's try it down here. So your beta negative, you get isotope 1 decays into isotope 2 plus your beta particle plus your antineutrino. So then beta positive, this is the antimatter version. Your beta positive is going to be your original isotope. Z is atomic number, A is mass number, X is your elemental symbol. So that'd be like what? That'd be like your chlorine, or so for up here, it's polonium here. That's your X. So you're going to have your original isotope. It is going to decay into C minus 1, same mass number, your new element, plus your, so this is called a positron, plus your neutrino. And a positron is the antimatter variant of the electron. So it's the same mass as the electron, same charge density, but it's everything about it is opposite. Its charge is opposite. It's the antimatter version of the electron. So what you're really noticing here is, so look up here. So your beta negative decay, a neutron becomes a proton. The neutron becomes a proton, and you end up with 7 and 7. Your beta plus decay, a proton becomes a neutron, and you end up with 5 and 5. Now you notice that 8 plus 6 and 7 plus 7 are both 14, and 6 plus 4 and 5 plus 5 are both 10. So the mass number doesn't change. It's just what's happening inside the nucleus. And when one of these particles becomes another, so like when a neutron becomes a proton, you get an antineutrino and a beta particle. And when a proton becomes a neutron, you get a neutrino and a positron, so an anti-electron. So that's your beta decay. And these are the three types of radiation that were noticed. So then came the experiments that gave rise to the idea of the nucleus of an atom, performed by Ernest Rutherford, where he fired alpha particles at a sheet of gold foil. Many of the particles just passed straight through, which is what he thought was going to happen with all of them. But then there were also many that were deflected at large angles, or were just completely reflected. And so this deflection and reflection told him, well, these atoms have to have a very dense center of very high positive charge. And through more experimentation, that's where he came into the model of the nucleus of an atom being composed of protons and neutrons. So neutrons have no charge. So the charge of the nucleus will be dictated by the protons, and you get your very dense, highly positive region that is going to be reflecting alpha particles, because alpha particles are also positively charged. And in electricity, positive is going to repel positive. So when we're looking at atomic structure, the part of the atom that we're the most concerned about is the electron. The electron is what does chemistry. Electrons will they're going to be what causes bonding. They're going to be involved in they're the main particle responsible for reduction and oxidation. They're responsible for Lewis acid behavior, Lewis base behavior as well. Um, And so they're just responsible for chemistry. But we do want to make sure we have all the information we need about protons and neutrons. So just like we did with the electron, the charge of the proton. So here's the symbol for the proton, but remember, it is the positive version of the fundamental charge E, and it is 1.60218 times 10 to the negative 19th, which you'll notice if we go back up and look, is exactly the same as the charge of the electron. It's just positive. So electron and proton have the exact same charge magnitude. Neutron is neutral. That's why it's called a neutron. And so, of course, here you see the symbol for the neutron that we'll use. When we're working with protons and electrons for ease, we're going to refer to electrons as a -1 and protons as a +1. This will come in handy when we're working with oxidation states, oxidation reduction reactions, and ionic charge calculations. So just there are times when you'll do calculations where you use the entire charge magnitude of an electron or proton, but most of the time we're going to be thinking of them in terms of -1 and +1. That's why like when you're working with your isotopes on your homework, you're going to think of them that way. So it's like if I have a neutral atom and it has 27 protons, that's 27 +1s. If it's neutral, how many electrons does it have? Well, it has to have the exact same number because that's 27 -1s. So you have 27 minus 27 gives you 0. That's a neutral atom. So then, of course, we gave the mass of the electron. Now compare these. You'll see that the mass of the electron is much, much less than the mass of the proton and the mass of the neutron. So, of course, there's your proton, there's your neutron, and there's their masses in kilograms that you can use for calculations when you need to. But elements on the periodic table also come in what's known as isotopes. Isotopes are going to be the same element. They're just they're different versions of the same element. And the reason they're different is because of neutrons. So your general symbol for an isotope is going to be your X with your Z as your atomic number, A as your mass number, and then X as your elemental symbol. And so the reason that neutrons are what make an isotope is because for an element to be an element, it has to maintain the same atomic number. If the number of protons changes, you don't have the same element anymore. So when you go to the periodic table and you see the elements listed in numerical order, 1, 2, 3, 4, 5, so on and so forth, those numbers are your atomic numbers. That tells you how many protons are in the nucleus of an atom. Well, the mass numbers are what change for an isotope. So if the proton number of protons has to stay the same, then it's the number of neutrons that has to change, and that's shown by the definition of the mass number. The mass number is your number of protons in your atom plus your number of neutrons, or you could say your atomic number plus your number of neutrons. So if that Z has to stay the same for it to be the same element, then the neutrons are what has to change for different isotopes to occur. So let's take a minute and look at some different isotopes. I again want to go over the naming scheme. So here we have carbon 12, carbon 14, and carbon 30, and chlorine 35. So this is how you name isotopes. And notice that the number on them is the mass number. So compare these symbols to that symbol there. So notice that your X is Cc and Cl. Your atomic numbers. Now look at the carbons. You notice how both of them have 6 as an atomic number? Well, that's because carbon has to have, so you see here, carbon has an atomic number of 6. If you get anything else, you have a different element. So if that changed to a 7, you no longer have carbon, you have nitrogen. So if you're working with different isotopes of carbon, that 6 has to stay the same. Same thing with chlorine. You have an atomic number of 17. And so anytime you're working with chlorine, that atomic number has to stay the same. Okay, so let's start breaking these down. So carbon 12, we say, well, it's neutral. So first off, how many protons does it have? Well, Z is 6. That's your number of protons. It's neutral, so it also has to have 6 electrons. 6 plus ones, 6 minus ones. Okay, then how many neutrons does it have? Well, your atomic number, let's do it like this. Protons plus neutrons equal the atomic number. Number of neutrons is going to be the atomic number minus the number of protons. Your A is your mass number. So for carbon 12, that's 12, minus your number of protons, 6. You have 6 neutrons. Well, let's think about carbon 14 again. For it to be carbon, your atomic number gives you your number of protons. It has to be 6. Otherwise, it's not carbon anymore. Since it's neutral, it also has 6 electrons. Your protons and electrons have to match to be neutral. You'll also take that into account when you're working with ions that are either +1, +2, -1, -2, so on and so forth. You'll have an imbalance of protons and electrons. Okay, so for neutral molecules or neutral atoms, you have to have the same number of protons, same number of electrons. Okay, well, how many neutrons does this have? Your mass number this time is 14. You're going to subtract off the 6, and you are going to get 8 neutrons. Okay, what about chlorine 35? So this time it's chlorine, so our atomic number, which is also our number of protons, is 17. So this number here, you can look at the periodic table and you can see it's 17. You can also use the periodic table to figure out what that atomic number would be if you're trying to finish off. Like let's say you have an isotope that only has the mass number, okay? Well, you're going to need to look at the periodic table, find the atomic number, and do your work from there. But since this is neutral, I also have to have 17 electrons, equal protons and electrons for a neutral atom. Okay, well, how many neutrons does this have? Well, that's going to be mass number minus the number of protons. The mass number is 35, minus 17 protons. You are going to have 18 neutrons. So this is how you start taking apart isotopes. But notice in particular the carbon 12, carbon 14. 6 neutrons, 8 neutrons. That's what makes an isotope, is the different number of neutrons. Okay, so maybe pause and work through these, and then restart, and you can see the solutions. So let's, how many protons and neutrons are there in the nucleus of each of the following atoms? These are all neutral, so in each, how many electrons are present? So we're doing the same thing as above. So let's go for A. You notice here how there's no atomic number at the bottom left? Well, this is why we have to use the periodic table. So we have bromine 79. That top number is still your mass number. The isotope name. So bromine, we can find right there. Bromine has an atomic number of 35, so I can fill that in. So, okay, how many protons? C equals the number of protons equals 35. Found that on the periodic table. This is neutral, so I also have to have 35 electrons. So there's part of the answer. Then, how many of each is, so how many neutrons? Okay, so for this one, remember protons plus neutrons is mass number. When you're doing your homework, I want to see you do these, no matter how simple it is, these derivations at least once, and then you can copy your equation through. Also notice how I've given this one, two, three, four, five different, so A through E. These will each be 1 point apiece because unlike your problems you have to work out where you have to give like a list, like what are you solving for, your list of knowns. Something like this is really too straightforward to give those lists. So if you see like A through E, you can go ahead and work them. Just make sure you're showing me everything you're doing. So our neutrons. And so now for the rest of them, you can just carry through this equation for neutrons. So our mass number, 79, minus the atomic number, 35. So we get 44 neutrons for bromine 79. So that's everything we need for that one. So let's go through that. Let's do the rest of them. B, I wanted to throw this one in here because maybe some of you have never seen it before. This is plutonium. It is down here. It is an actinide. So every now and then I'll throw something in there where you're going to have to really search the periodic table. Yeah, but it builds skills. So again, we don't have the atomic number. So we look it up and we notice that the atomic number, which is our number of protons, equals 94. In a neutral atom, that means we also have to have 94 electrons. So there's part of our answer. Now, how many neutrons? So this is going to be our mass number A, 239, minus our number of protons, which is 94. We are going to get 145 neutrons. And plutonium is something you want to stay far away from. That will make you glow. It's also what's in many nuclear warheads, so it's not a very friendly element. Okay, so C. This one I also put in because it's fun. Okay, hydrogen 3. This is radioactive hydrogen, or also called tritium. Okay, so we find hydrogen, and we notice that it has an atomic number of 1. So we have 1 electron. For it to be neutral, we also have to have 1 electron. 1 proton, 1 electron. And now the number of neutrons, it's going to be the mass number minus the number of protons, or 3 minus 1. We have 2 neutrons. Okay. So D, here we have iron 56. Okay, so we find iron, that is a transition metal. So these columns that are higher, here, here, that's main group. Those groups have names. Everything in between there, those are your transition metals. We'll talk about that more in detail on Monday, but that can also help with a homework problem. Uh, this group here, your 17, that's your halogens. Okay, so for iron 56, iron we notice has 26 as its atomic number. So the atomic number equaling the number of protons equals 26. For a neutral iron atom, we also have to have 26 electrons. And what about the neutrons? Mass number minus the number of protons. The mass number is 56 minus the 26 protons, and that is going to give us 30 neutrons. And the last one, E. Okay, this one is, so CS is cesium 133. Where's cesium? Cesium is right here, group 1. Remember, your columns are your groups or families. So cesium-133 is fun because this is the atom that runs, this is the isotope that runs the atomic clock. So basically all of your GPS is set to this isotope. And what it does is the very outer electron of this isotope will jump between quantum levels. And when it jumps, when it it goes up in energy and then goes back down. And when it goes down in energy, it releases photons. And it does this at such a steady frequency that that what we know as the second is based off the number of oscillations of that outer electron. And it's a stable isotope, so the cesium-133 is not going to decay. Um, I was looking it up. If it has a half-life, it's very, 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 very long. So you can really just think of it as not decaying. Okay, so but we say cesium has an atomic number of 55. So the number of protons is 55. For a neutral atom, that also means 55 electrons. 55 plus ones and 55 minus ones. The number of neutrons is our mass number minus our number of protons. That is going to be 133 minus the 55 protons for 78 neutrons. So that's how you take apart isotopes. You want to remember the common format for how isotopes are written. Your top left number is your mass number, your bottom left number is your atomic number. If that's not there, go to the periodic table. The atomic number tells you the number of protons. For a neutral element, it also tells you the number of electrons. So you have to have equal electrons and protons. And then to find neutrons, you just subtract the protons off the mass number, because your mass number is protons plus neutrons. All righty, and that takes us through to the end of today, and I will talk to you all next week.